Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on aside as we conclude Chapter 5 in the Big Ideas Math Integrated Math 1 textbook. This is on the Chapter 5 test and cumulative assessment. 15 questions on the Chapter 5 test, 10 questions on the cumulative assessment, all ranging from questions from chapters 1 through 5. They generally backload chapters, 5 questions in that mixed review. What I do like about this one, and I don't know, I haven't actually seen the questions themselves, but what I'm anticipating from the Chapter 5 test is mixed review so that when we solve systems, we can probably choose a method, substitution, elimination, or graphing, that they might have no solution, infinite number solution, special cases sprinkled within, and they won't warn you about it. So something that we didn't get before. Something that we were in the vacuum of the section itself. Even in the previous reviews, it was within that particular section that they said they were in. So I think here it'll be pretty nice to see that. Jump to the description section down below so you can find this PDF, or the PDFs I should say, because they're for the two separate parts, as well as graph paper, because of course we're going to be graphing. If not solving systems by graphing, we will be graphing systems of inequalities, or inequalities in general. So I'm going to go ahead and get started with this one. Numbers 1 through 6, or 7, 8, I don't know. Solve the system of, here it is, solve the system of linear equations using any method. Explain why you chose the method. I'm probably going to do one method per problem here. So for this first one, 8x plus 3y equals negative 9 and negative 8x plus y equals 29. These are in standard form. 8x and negative 8x are already additive inverses of each other. This is textbook elimination method kind of problem. If I add right now, the x's are gone. 3y plus y is 4y, negative 9 plus 29 is 20. Divide by 4, get y equals 5. Oh, I didn't mention this yet. Less teaching, more doing on these problems, of course, right? We're now at the final part of this. Substitute 5 for y. Let's do the top one. 8x plus, this is probably the harder one. 8x plus 3 times 5 is negative 9. I was so turned away by that 8x being negative on the other one, but that's okay. This is negative. Now I have to do this. Negative 24, I think that is in this. X is negative 3. So we have a ordered pair of negative 3, 5. So I chose elimination for that one. I think it was pretty well set up for that. Number 2, normally I don't opt to solve by graphing, but number 2 already has fractions involved, and one of them is already in slope-intercept form. The other one's well on its way. Just because I don't know if I'm going to solve by graphing from other ones, let's go ahead and solve this one by graphing, guys. Let's do, why it's 3/5. Yeah. Let's solve this by graphing. So I'm going to rewrite this top equation. I'm going to solve by graphing. Rewrite this top equation by subtracting 1/2 x from both sides. Now, my only hope is these intersect within the scale from negative 10 to 10. I have no idea if they do or not. So let's go ahead and see what this will look like as a graph. I'll do the top one in blue and the bottom one in green, okay? So here, it's just because those fractions and one's already in slope-intercept form, and I don't know if I'm going to be able to do graphing later. This one seems most appropriate here. Your final answer should be an ordered pair regardless, but graphing's a good reminder that, yep, of course we should be doing that. Oh, hold on, that's set up from a previous video I did. Let's do solid line there. There we go. All right, we are going to do some dashed lines ultimately. All right, 3/5 x plus 5. So up 3, right 5, sure, but down 3, left 5. Will I fit? Oh, will it hit it? Yeah, I think right there. Boom. I think that's where we actually hit this one. So the ordered pair here is negative 10 for x. Oh, that didn't change still. Negative 10 for x, negative 1 for y. So there's my solving by graphing for this one. Would have substitution been faster? Depends on how fast you are working with fractions, either dealing with them or busting them. In that case, I chose to graph. That's how I dealt with my fractions. All right, y equals 4x plus 4 and negative 8x plus 2y equals 8. Given that this y is already by itself in this equation, I'm going to go ahead and use substitution. I'm going to take 4x plus 4, substitute it for that y in the other equation. I have negative x plus 2 times 4x plus 4 equals 8. We can distribute the 2. That's a lot of things. Oh, take a look at this. This is one of those cases. Negative 8x plus 8x is 0. So we have 8 equals 8. That's a true statement. This is infinitely many solutions. So this has done everything that I've wanted to so far in the first 3 problems. I've gotten to choose methods, and so far I've chosen all 3, and I've had a special case. Pretty cool. Number 4. Also opting for substitution on number 4, given that x is isolated. X equals y minus 11, and this is x minus 3y equals 1. Let's substitute y minus 11 for x down in this equation here. We will get y minus 11 minus 3y equals 1. By the way, I didn't write this before, but that's a substitution. S, that's an S, not a 5. Y minus 3y is negative 2y. I'm going to go ahead and add 2y to both sides and subtract 1 from both sides, and I'll get y equals negative 6. Not done. We still need to find x. Right here, negative 6 minus 11, which is negative 17. I don't know if I had any want to solve this by graphing, but it's a good thing that I didn't, because this would have been outside of my window range of negative 10 to 10 if so. So I didn't, and I shan't. That was substitution. Number 5 looks like it's lending itself to elimination method. I wouldn't want to use substitution in a case like this. No matter what variable I'd try and get by itself, it would always have fractions. And y-intercepts, if I wanted to solve by graphing, it would have fractions. Fractions for slopes are fine. Fractions for y-intercepts, a little less so. Now, I'm seeing something of this problem that I'm not going to call attention to yet, but I am going to use the elimination method. Now, what I'm going to do is, well, I can't divide. Is that a 9? Yeah, I can't divide by anything there. These could divide by 3s. I don't know if that really helps anything here. See, I can't multiply anything here to cancel anything out. So let's at least divide by 3 to begin with on this set. How about negative 3? To get ourselves in tune with what we want. So negative 3x plus 2y equals negative 5. Now we can see that here we can double these values here. And actually, I think everything's going to kind of cancel within. So now we're going to get negative 6x plus 4y equals negative 10. So ignoring these 2 equations for now, because I'm going to add down these lists, x's eliminate, y's eliminate, you get 0, and 9 minus 10 is negative 1. So if you have that, it's a false statement. That is a no solution case. Now, there are different ways to go about that, right? I did use elimination, and I would still use elimination. But I could have also found the least common multiple here. I could have multiplied this by, say, 3 and by negative 2 and eliminated y's. X's would have eliminated as well. But, you could have multiplied. I decided to go with division, and that was my choice. Number 6, because I don't trust whether the graphs would intersect within my window range or not, I'm not going to solve by graphing. I'm going to go ahead and use substitution here because that y is isolated. And you know what? This is a nice antithesis to the, not the chapter review, to the quiz, the 5154 quiz, because there were very few problems, I'm going to use substitution, there were very few problems I solved by substitution when I had a choice. So here there are significantly more than the elimination. So I'm getting a nice barrage of those. Negative 4x plus 5x is x. Add 7, you get 6. Y, let's substitute right here. We get 5 times 6 minus 7. 30 minus 7 is 23. So that is outside the window range. It's a good thing I didn't go for any sort of graphing on that one. So 623. So there are the first 6 problems and the methods that I chose. Again, elimination, graphing, substitution, substitution, elimination, substitution. So I got a few more substitution there than I generally would have. Number 7, write a system of linear inequalities. This is completely unrelated. Write a system of linear inequalities so the points 1, 2, and 4, negative 3 are solutions. I'm going to get graph paper for this. Are solutions, and negative 2, 8 is not. This is open-ended. Excuse me. Really helps to have the graph in these cases here because then you can kind of create a boundary line based off that. So I'm going to put in green what would be a solution. 1, 2, and 4, negative 3. And then negative 2, 8 is not. Negative 2, 8. Now I could take the easy way out, and I could say, hey, x is greater than 0 is an inequality. Oh, it's a system of inequalities, right? Now I could take the easy way out, and oh, geez, that's going to be... Well, here's the thing. It just needs to satisfy this... Okay. I'm going to do a vertical line because we don't see vertical lines very often. So I'm going to do one. I'm going to do a vertical line that's x is greater than or equal to negative 1. So it's going to look like this right here. So this is one of them, and it already satisfies this part. greater than or equal to will mean to the right of it. So x is greater than or equal to -1, already satisfying that. Now this next one, as long as it satisfies this, it's cool. It can also satisfy the one in red, but because it's a system, it needs to at least satisfy the other. So this one I'll do a little bit more like diagonal-esque. Let's do like a down 2/3 kind of thing like this. So y is greater than or equal to -2/3 x plus -5. Or how about greater than? Let's do one that's specifically right. This is so open-ended here, guys. I hope it's okay that I'm doing that. So this one I'm going to do, that boundary line is -2/3 x minus 5. And this can be my system like this. To be greater than this is to the right of the green, and to be greater than this is above the blue. So my overlapping shaded region, the one that matters for me here, is going to be this guy right here, which uses these as solutions to the system, and the red is not. Despite the fact that it's above the blue, it's not to the right of the green. Now, did I do all that right? System linear inequalities, so those points are solutions, but -2, 8 is not. Okay, that's good. Now, I could have done a horizontal line, made it pretty easy for myself, but I left it. Okay, number 8. How is solving the equation here by graphing similar to solving the equation there by graphing? How is it different? Well, I don't know if we actually have to solve. So I don't think I'm going to actually solve, just for the sake of it. When I'm doing, I'll at least type this out, but the absolute value of 2x plus 1 equals the absolute value of x minus 7 differs from 4x, no, is similar to 4x plus 3 equals -2x plus 9, because we are, in that, we are seeking the x coordinate of the point of intersection, point or points of intersection of the equations. By creating a system, right? By creating a system of equations. Setting y equal to the left and right expressions. So we create a system of equations. If we're solving by graphing, we create a system of equations. We set y equal to the left side, y equal to the right side, and then we find out where they intersect. Y equal to left, y equal to right, figure out where they intersect. But we find the x coordinates. Now, where they're different in the absolute value portion, the absolute values equation differs in that there are two systems involved when creating the conditions for the positive and negative versions of the absolute value. So I'm not doing it here, but what I would do here is I would just do y equals this, y equals this, y equals that, graph them. Here I'm going to do y equals this, y equals that, and graph them. And then I'll do y equals this versus y equals the opposite of this, which is -x plus 7. And then you graph those as well. So because we have more than one answer there, we have two systems in that case. That's going to make that so. I'm not actually solving, they said explain. Number 9, maybe we have to do some later. All right, graph systems of linear inequalities for numbers 9 through 11. So on number 9, we have y is greater than 1/2 x plus 4, and 2y is less than or equal to x plus 4. This one's incredibly close to a slope-intercept form, so I'm just going to go ahead and divide it by 2, and now it'll say y is less than or equal to 1/2 x plus 2. So 1/2 x plus 4, 1/2 x plus 2, they're parallel. Does that mean there's no solution? Maybe. I think this case it will have no solution, but that's not always the case. Depends on where the lines go and where we shade. So the first one, 1/2 x plus 4, looks like that. We will be shading above, and this will be a dashed line. So allow me to kind of draw the line first. I'll dash it up after that. Oh, it is already dashed. Never mind. Pre-made. We'd be shading above this guy, right? I'll just do kind of a rough version of it because this will not overlap with this next one. Next one is less than or equal to 1/2 x plus 2, and that's right here. So it's parallel. And it's a solid line at that, but we will be shading underneath this one, where 0, 0 would be a true statement for this one, but not the other one. In fact, anything that's a true statement for this one is not a true statement for that one, and that's kind of the point of, hold on, make it solid. And that's kind of the point of, ooh, make it green. It's kind of the point of the fact that there's no solution to this case here. One is above, one is below. This is a very special case where there's no overlapping shaded region. This one we'd be like that. Because it's just above and below like that, this is, y'all, a no solution. We should identify it as such. Only with overlapping shaded regions. It's weird that the first one we did was no solution, but hey, I think at this point it's just test. It's not so much, here's a progression system. I don't think they're working toward going harder. They're just giving you what they give you. So the next one has x plus y is less than 1, and 5x plus y is greater than 4. First one I'm going to write out a standard form, or keep in standard form. This one I'll put in slope-intercept form. Let's make that green. Okay, so for this next one, x and y intercepts of 1, they're very close to each other, so this will be a little tricky. So I got to make sure that slope of -1 is worked out right. So I got to go, is that right? Ah, that's not even close to it. Excuse me. I just ate, so y'all, I'm going to have some weird hiccups. Okay. I always stuff myself with food before recording sets of videos. Not always true, but in this case, totally. Okay. Less than, jeez, I'm going to sip some water in a second. Less than, we are going to shade underneath. I have to take care of my hiccups here in a second. Apologize for the weird dark spot that's happening because I lifted up my pen. Anytime I now lift up over here, it's always going to overlap and be a little bit darker. So things happen. Okay. Less than. I said less than we shade underneath. I shouldn't have stated that. Only when y is by itself can you do the less than, greater than, shade underneath versus or whatever. But given that y is positive, we would. Or given when you test 0, 0, it works. So there's that. The next one is going to be y is greater than -5x plus 4. So this is down 5, right 1. It's okay that these don't intersect at like a perfect place or anything like that. It's just about overlapping shaded region anyway. So also a dashed line. Less than is it's greater than. Greater than is above, and being above, technically it's to the right. So over here on this side. Now the overlapping shaded region is this one right down here. That's the one that we care about for solutions, which doesn't include 0, 0, by the way. But it's that set right there. So if I were to pick a point that was a solution, for example, 4, -5 would be 1. Did you do? But it's just that whole set, right? Anything within here. Now, what I've been doing recently for these, you're going to have to ignore, again, this little part right here. But for the chapter review, I made this all black and white to really show the darkened portion. This darkened portion is the solution set right there. Anything right here is not the solution to the system. Okay, number 11. I'm going to put them both in slope-intercept form. You know, I expected some of these, and they just didn't happen. Maybe there's still a chance later. But I expected to get some y values that were negative, where when writing in slope-intercept form, we had to divide by a negative, which means we had to flip the inequality. That's not going to be the case here on the bottom. But I am going to get in slope-intercept form. So on the bottom, I'm going to rewrite this as y is greater than 3x minus 2. Let's go ahead and graph both of these. So the first one, this time what I'm going to do on these as a whole is I'm going to just draw the boundary lines and then I'll shade at the end. So down 2, right 3 looks like that, and up 2, left 3 looks like this. And it's a solid line, and eventually I would be shading above. Eventually I would be shading above. I'm going to save it, pocket it. Y is greater than 3x minus 2, something else to shade above, but with the dashed line and with this boundary line. Up 3, right 2, or up 3, right 1 from -2. There we go. We will make this one dashed momentarily. And we're going to shade above this one as well. So what is above each of these lines here will be this shaded region, or will be this region right up here. That'll be the overlapping shaded region. So this guy. What is two thumbs and an overlapping shaded region of the system of inequalities? This guy. Yeah. All right. So that's number 11. Number 12. 12 through 15 all look like word problem bases. You pay $45.50 for 10 gallons of gasoline and 2 quarts of oil at a gas station. Okay. Your friend pays $22.75 for 5 gallons of the same gasoline and 1 quart of the same oil. Is there enough information to determine the cost of 1 gallon of gasoline and 1 quart of oil? Explain. Yeah, there should be. We can create a system of equations. Nothing's... Oh. I have to think about it because this proportionally, 10 gallons of gasoline, 2 quarts of oil, 5 gallons and 1 quart of oil. Oh, because we know 1 quart... let me think about it. Maybe not. Maybe not for this one. No, because when I write... I'm sorry. I was thinking that slopes were different, but now when I do a division, that's not the case. So here's the thing. Let's let... This is a system. I'll do X. X equal cost per gallon of gasoline in les dollars, and Y is cost per quart of oil. So here's the problem with this one. When you set it up as a system of equations, we're going to have a 10x plus 2y equals 45.50. And then we have a 5x plus 1y equals 22.75. 22.75. Now, before I was saying, oh, slopes are different, 10 and 5. I didn't realize that this was a 2y right here. So the problem is, whether you write it in slope-intercept form, whether you divide this top equation by 2, whatever it is that we see here, you're going to notice that this is literally the same equation back out. So 22.75. It's basically, I bought double the stuff, and I paid double the amount. So it doesn't get me what each individual one would be in this case. So for part A, no, this is an infinitely many solutions case here. We still don't actually know the set. No, this has infinitely many solutions. It's the same line. All right, part B. The receipt shown, oh, we got a receipt here. The receipt shown is for buying the same gasoline and same oil. Is there now enough information to determine the cost of 1 gallon of gasoline, 1 quart of oil? Explain. I can't tell how many gallons of gas they did. Oh, that's 8? I thought that was $8. I'm sorry. That's 8 gallons of gasoline. Okay, so yes, now there would be enough here because we have 8 gallons of gasoline. And you might not be able to see this, but let me copy and paste it. I thought this said... Oops, not over here. I thought this said $8 for gallons of gasoline. So it's 8 gallons of gasoline and 2 quarts of oil. Total, we pay $38.40. So yes, this is going to give us a different setup. It says determine the cost of 1 gallon gasoline, 1 quart of oil. So anyway, so for part B, there's my setup for one part there. Yes, we now have enough information. Different equation. Different equation means different information, different expressions here. We didn't just double up or triple up the amount that one other person did or something like that. So part C is solving. So we have 8x plus 2y is 38.40. Here's the thing I'm going to do. I'm going to do it with the small one right here. I mean, that's the same equation as this, right? I'm going to divide this one by -2 because that will eliminate our y's, and it does it with smaller numbers. So now this will be -4x minus y equals -1920. And then this one up here, 5x plus y is 22.75. This will solve for x right here, 1 gallon of gas. 1 gallon of gas is $3.55. That's nice. I don't know where your part of the world or country is for gas. Ours is like $6 where I live. So $3.55. To figure out a quart of oil, we have to do some sort of substitution somewhere. So I can do like 5x plus y. 355 plus y is 22.75. Let me use the calculator here. 5 times 355. Of course, it's frozen. Let's see. Come on. 5 times 355. And then subtract 2275. I'm going to do it all in the calculator right now. Oh, is that $5? I think it's 1775. So I got 1775 plus y is 2275. Subtract 1775, that should be 5. So x is 355, y is 5. We don't write this as an ordered pair. We're going to say each gallon of gas costs 355. Each quart of oil costs $5. All right. Okay. All right, here we go. Number 13. Describe the advantages and disadvantages of solving a linear system of equations by graphing. I've stated a lot of them out loud. Now I got to kind of get into it here. So I have a nice big pros and cons list. Hold on. I'm going to cheat a little bit. I'm going to find one of my old... Oh, do I have it on here? Pros, cons, system. I'm going to look up... I do have it. I'm going to cheat so much right now, guys. I have an old pros cons list, and I have it on a video, so I have a file for this thing. I'm just going to copy and paste into here. It's going to be a big, exhaustive list, though. I don't want to miss anything, miss out on anything. Now, this pros and cons list also has substitution and elimination on it, so I'm just taking these ones here. I'm just going to read them out loud and such. I have a whole video that does a whole bullet pointing thing of these. You can probably find it. It might be called the pros and cons of methods of systems of equations, All right, so fitting them all on here. It's a little cheating, but it's something I've done. I made this. So pros: you can see your solution set as it naturally exists as the ordered pairs. It gives you a true idea of what your solution really means. In an infinite solution set, infinitely many solutions, same line, no solution is parallel lines. Okay. Easy to work with when equations are written in slope-intercept form, even when they're fractions. I think I did that on number 2, right? When they were fractions, that was okay. It also has quick solving abilities when written in standard form, that you can get y by itself in that way, or you can use intercepts for that. In certain real-life contexts, the graphs often tell a story about the nature of them. That's been especially true for systems of inequalities. I mean, we'd have to graph those anyway, but they tell a nice story as far as rates and when something's under something else. You know those how do you see it equations? Those ones often are contextual, and those ones we get to see things on a graph, like when something's under, it's when it's less than, and things like that. I really like those. It's a viable method to solve past linear systems. So when you start solving quadratic systems, rational systems, things like that, if you ever do, it's very viable for that one. Okay, cons. It's not easy to determine, and I've mentioned all these. It's not easy to determine the solution if the lines do not intersect on integers. Sometimes it's darn near impossible. What if they intersect at 2/7? How can I tell 2/7 versus 1/3 when it comes to those kinds of things? Those are terrible. So integer values are good. They must be drawn to scale and within grid lines. Thankfully, I've been having my own sets of, graph paper like this. That's good. But, you have to make sure that you have that. Otherwise, if you have binder paper and you create your own axes, that point of intersection might not look like what you expected it to. If points intersect far away from your graphing window range, you're unlikely to be able to reach its point of intersection with precision. I did that literally. I forget if that was on this video or not, but there was one where we had like 623, and I was like, thank goodness I didn't have to graph that one, because I wouldn't be able to find that one, or I have to change the scale. Not all equations are written in slope-intercept or standard form, and it's not readily graphable if desired. And that's the thing. I think we had another question up here. This one right here where I said the y-intercepts would be fractions. It's in standard form, but the y-intercepts would be fractions, and that's icky. But yeah, if they're not in slope-intercept or standard form, it's not in a graphing form for you. And it can also be difficult to work with there. And in word problems where variables are not denoted as x and y, the graphing axes now require precious labeling and can bear little or insignificant importance from the student's viewpoint. So if we're talking about, berries and grapes and finding their point of intersection and things like that, you have to redefine them as x and y or call them b and g and make sure that you understand what it means for this to be higher up versus that. Now it's berries and grapes. It's not time and distance, and it just gets a little weird in those scenarios, or just x and y straight up. So that's my pros and cons list. I explained it all. I was like Clarissa, baby. You can find that old video as well where I totally bullet point those in greater detail. Number 14. You have at most $60 to spend on trophies and medals to give as prizes for a contest. This sounds like inequalities. Write and graph an inequality that represents the numbers of trophies and medals you can buy, identify, and interpret a solution of the inequality. So this time we want to use x and y because we're talking about, graphs. X is number of trophies and y is number of medals purchased, whatever. So let's create an inequality set here. $60 to spend. Oh, right in here, trophies. I don't know if you can see it. Trophies cost $12 each. So I can do 12 times X to get how much I spent on trophies. Medals cost $3 each. I thought I was going to have to make them up. Plus 3 times Y, and I can spend at most $60. So I have to stay less than or equal to 60. Here's my setup. It says graph this thing and interpret a set here. Now, as far as my graph goes, I'm going to go based off intercepts here. I have a y-intercept of 20 and an x-intercept of 5. Divide that by 3, divide that by 12. I'm going to be shading underneath U-test 0, 0. That works out, and 0, 0 will be underneath this graph. I'm going to do a... Oh, I got rid of my... No. I got rid of my graph paper. Hang on. The one that I borrowed as an example, I deleted from memory. I'm going to use the first quadrant only, so I'm going to do a couple of things here. Sorry, I got to play with this. There we go. And I got to change the scales. My y is going by 20s, how about? Or by 2s. So 10 and 20. X's, I'll do the same. X, I'll just leave as that, all right? This is 10 and 20. So y-intercept of 20, x-intercept of 5. Be very, very careful. Y's are going by 2s, x's are not. So less than or equal to, the shading will be underneath. And I'm going to be in the first quadrant only. You can't buy negative metals, anything like that. So my shading is just within this range right here. I can buy 0 metals. I just can't purchase negative amounts of them. So, as I'm getting prepped to sketch, sorry, I have to change all the thickness and the transparency and stuff. Probably still a little too thick. Laying it on a little thick there. This is my set. Accidentally lifted. Let's do that one more time. I feel a little responsible. Not within the lines. Super apologies. Okay. So with this in mind, I need to get a new pen tip. So with this in mind, it says identify and interpret a solution of the inequality. Let's say I do this one right here. Keep in mind x's are scaled by 1s and y's are scaled by 2s. So this is 1, 12. This solution means that I can purchase 1 trophy and 12 medals and still stay under budget. I can afford to purchase 1 trophy and 12 medals. Now, is that the only solution? Heck no. There are a bunch of them. There are a bunch of them within here. Pick a point, pick a set, and go. But that's part of part A. Part B says you want to purchase at least 6 times. Write and graph a system that represents the situation. How many of each item can you buy? Wait, what? You want to purchase at least... Oh, 6 items. I thought it said 6 times. I was like, what are you talking about? Well, I can do this one. It says write and graph a system that represents the situation. Oh, got it. Okay, so we have to go into this a little bit more. So we have that first one, which is the 12x plus 3y is less than or equal to 60. So part B, 12x plus 3y is less than or equal to 60 is our first one. Stay within $60. We have to purchase at least 6 items. So this sum of medals and trophies must be greater than or equal to 6. So it says how many of each item can you buy? Let's do this. X-intercept of 6, y-intercept of 6. Keep in mind the y-intercept right here and x-intercept right here of 6 would look like that. Okay. So, and greater than or equal to means 0, 0 is not a part of it. We'd have to be shading above. So if you don't mind, I'm just going to basically erase this. Oh, that looks weird. I'm just going to erase this part right here. And then what's inside the shaded region right there is all that matters for us, like that. Okay. So it says, how many of each item can you buy? I think it's just picking another point of things that work for this thing, right? I can pick another set and see what works. For example, I can do And go over 2 and up, say 8 right there. So we can do 2 comma 8 for part B. That'll work. As long as I purchase at least 6 items, right? 2 trophies and 8 medals will do. Last one on the chapter tests. Number 15. Compare the slopes and y-intercepts of the graphs of the equation of the graphs of the equations of the linear system. In the linear system, 8x plus 4y equals 12 and 3y equals negative 6x minus 15 to determine whether the system has one solution, no solution, or infinite many solutions. Yeah, a lot of these we don't have to graph if they're parallel. Then we've got to see if the y-intercepts are the same or different. And that's what I want to do. I'm going to get these in slope-intercept form. Let's get y by itself here by subtracting 8x and then dividing by 4. We get negative 2x plus 3. And then on this one here, if I divide everything by 3, you get y is negative 2x minus 5. Slopes are same, but y-intercepts are different. That means that these are parallel lines. Parallel lines are no solution. Okay, no solution. That's why, and that's how we compare them there. Okay, guys, I'm going to pause really quickly, and then we're going to get to that cumulative assessment. Hang on. Okay, I noticed my screen behind me blacked out. It's baseball, so on to the Giants game we go. All right. Okay, guys, we are going to now jump into the cumulative assessment. There are 10 questions in total. These can get a little weird as far as questions go. We'll see how they answer. I'll try and identify which chapter it's from. For the most part, it's pretty easy. Normally, they start off the current chapter, so we'll see how we go. Let's go ahead and get started. The graph of which equation is shown? Oh, well, that's not from this chapter. That would be chapter 3. We graphed in chapter 3. So number 1, the graph of which equation is shown here. I'm going to determine based off of intercepts. So when I'm looking at this, I got an x-intercept of 2 and a y-intercept of negative 9. Now, instead of actually rewriting these in slope-intercept form and doing that, just divide this by 9 and you get negative 2. No. Do this by negative 9, you get negative 2. No. Divide this by 9, you get 2. Yes. Divide this by 2, you get positive 9. No. By negative 9, you get 2. Divide by 2, you get negative 9. Yes. So it's going to be D, and I'll show you that work. I just didn't want to do it on all 4 of them. So negative 9x plus 2y equals negative 18 gives you that. You see for the x-intercept, you have set y equal to 0 and divide by negative 9, you get x equals 2. Y-intercept set x equal to 0. Divide by that and you get y equals negative 9. So it's going to be D, like that. All right, number 2. A van rental company rents out 6 minus. Those are just hyphenated. 6, 8, 12, and 16 passenger vans. The function c of x equals 100 plus 5x represents the cost c in dollars of renting an x passenger van for a day. Choose the numbers that are in the range of the function. This sounds like chapter 1. So we have c of x equals 100 plus 5x. To stay within the range, x is the passenger van things here. So our range is by substituting those values in our domain. So with we'll do c of 6, c of 8, c of 12, and c of 16. So for all these, it's a substitution. That's 100 plus 5 times 6, or 100 plus 30, which is 130. And this is what? The cost? The cost of renting it. So $130 is in the range. 5 times 8 is 40, so this gives you 140. Do these all go up by 10s the whole time? No, because the spacing is a little different now. So 100 plus 5 times 12. 5 times 12 is 60, so this is $160. And then 100 plus 5 times 16. 5 times 16 is 80, so this is $180. So these are our range values. Like that. Number 3. Fill in the system of linear inequalities, chapter 5, with a less than or equal to, greater than, or greater than or equal to, so the graph represents the system. Now, both of these look like they're above the lines, and because they're y in comparison to them, they will both be some form of greater than. The question is, hold on, I tried to put D. I tried to use a shortcut to copy this equation set, although I absolutely could just write them down. The question is, which one is the or equal to here? Because that's kind of what's involved. This solid line is the greater than or equal to. Looks like it has a positive slope and a negative y-intercept, so that looks like the first one. This is a greater than or equal to here. The other one must be the greater than. It is above, but it's a dashed line. It's a negative slope and a positive y-intercept like that one is. So this one must be greater than a number 3. Number 4. Your friend claims to be able to fill in each box with a constant so that when you set each side of the equation equal to y and graph the resulting equations, the lines will intersect exactly once. Do you support your friend's claim? Explain. I do not. I do not support my friend's claim. When we have the same slope on both sides, right? The idea of graphing these ones is make them say y equals this and y equals that. Y equals 4x plus this, y equals 4x plus that. If I give them the same value, they will intersect all the time together, infinitely many solutions because they have the same slope. If I give them different y-intercepts, they will never intersect at all because they're parallel lines here. So I do not support my friend's claim that there is absolutely no value where they'll intersect just once. I do not support my friend's claim. Each side of the equation contains the same slope. Therefore, constants must, therefore, any substitution there constant-wise, you can only obtain no solution or infinitely many solutions. You cannot get exactly one. Silly friend. I don't know what they're going on about these days. Number 5. The tables represent the numbers of items sold at a concession stand on days with different average temperatures. Determine, oh, this is like that stats stuff. I forget what chapter this was, though. I think 3. Well, no, it might have been 4. Determine whether the data represented by each table show a positive, negative, or no correlation. Now, I don't know if I fully intend on plotting these points without using a graphing calculator or rewriting them in order and such, and I think that would really help if I did. So when I look at, yeah, these are out of order. If I do anything with these guys, folks, you guys, I will likely use a graphing calculator and not plot these because they're just a little, yeah. You know what? I'll go ahead and plot them. Why not? The only problem is that first quadrant biz. Hold on, let me find the ones from the old set. Let me do a first quadrant bit here because I think all these are only positive, right? All right, so with the first one, I'm scaling, I'll scale the y's by 5s, so I'll go up to 50, and I'll scale the x's up to 100. So let's see what these do. 14, 35, 27, remember these go 10, 20, 27, and then we go 28, because these goes by 5s. That's the tricky part here. 32, 22. Sure, this won't be perfect, but sure. This so far looks like a negative correlation. 41, 9. Oh, the x's are increasing. I thought these were random. I'm sorry about that. I probably didn't need to. I'm not going to keep graphing these guys. Oh, yeah. Okay, this is a negative correlation. I thought these were scattered order. I should have looked at them harder. This is a negative correlation. X's are increasing as Y's are decreasing. I guess I might as well finish this one while I'm here. 41, 9. I complain and then I do it anyway. 48, 4. 62, 2. 62, 2. 73, 1. Sure, like that. It's kind of a strange, different kind of look, right? But you can draw a line through it. That one's negative. The next one, you can tell as x's increase, y's also increase straight up. That one's going to be a positive correlation. I'm going to go without the graph there. Now, is it a strong correlation? I wouldn't consider that first one to be very strong, at least not for a linear equation. I mean, it's there. There's a correlation. It's clearly negative, but it's not the best fit of all the points on there. This one's going to be positive. x's are increasing as y's are increasing. So I did one of the sets of points. We can see that through there. This one will be the same thing, only positive. I thought the x's were in a scattered order. Totally not. All right, number 6. Which two equations form a system of linear equations that has no solution? We're trying to find ones that are parallel. If they're in slope-intercept form, we're trying to find two that are parallel and have different y-intercepts. Same slope, different y-intercepts. Y equals 3x plus 2, y equals 3x plus 1/2 have the same slope and different y-intercepts. So these are the ones that have no solution. That would be this chapter. Same slope, different y-intercept. Number 7, fill in a value for a so that each statement is true for an equation. This must be chapter 1. I'm not going to solve by graphing. I'll solve algebraically. Ax minus 8 equals 4 minus x. When a equals blank, the solution is x equals -2. Okay, this is interesting. So let's do this. Let's add this x over. We have ax plus x. Let's add the 8 over and we get 12. Now remember, this is a 1x such that if I factored in x out, this might be old school for you guys to not really remember what's going on. I'd get 12 right there. And so x would equal 12 over a plus 1. So let's look through this and get our solutions that we're looking for. Part A, for x to equal -2, we have to set -2 equal to 12 over a plus 1. Now, there's not a lot that you necessarily know about having variables in the denominator, so I'm not going to speak on it as we haven't talked about it. So let's kind of play some guess and check. 12 divided by what is -2? 12 divided by -6 is -2. So a plus 1 has to become -6. Subtract 1, a has to be -7. So the answer to part A is -7. Again, a little guess and check there. We're going to have to do that kind of for all of these if that's okay. So for part B, for x to equal 12, we need 12 to equal 12 over a plus 1. Well, 12 divided by 1 would give us 12. Therefore, a plus 1 would have to be 1. Therefore, a would have to be 0. So again, I guess I'm not playing guess and check, but I'm saying 12 divided by what number gives me 12, and then that's where I can come up with my equation on that. Part C, for x to equal 3, 3 equals 12 over a plus 1, and 12 over 4 is 3 in that case. So a plus 1 would have to equal 4. Therefore, a would have to equal 3 as well for x to equal 3. Okay, now that's not something I'm double checking with the original. I did the rewrites for it. It should work itself out just fine on those. Number 8, which ordered pair is a solution of the linear inequality, current chapter, linear inequality whose graph is shown? It said which of them is, so it sounds like there's only one answer. 1, 1 is a no-go. You can tell, well, let me cross out the A. Is a no-go. You can tell that point's right here. -1, 1 is on the dashed line. That is also a no-go. If it was a solid line, sure. -1, -1 looks good, so I'm going to go ahead and qualify that one. It's probably the only one. And then 1, -1, yeah, that's also a no-go. So it's going to be C, -1, -1 is the solution to that. Now, they didn't ask us to write the inequality, but you could use slope-intercept form and figure that one out. I believe it's supposed to be y is less than -2x minus 1. I think that's it. So -1, -1 is a solution. Check it out. Because we get -1 is less than 2 minus 1, which is 1, and that's true. Okay, number 9. Which of the systems, this current chapter, which of the systems of linear equations are equivalent? A what? So I don't know if we're going to have to do like a solving thing or just rewrites of them. Oh, this might be like that question where maybe you can add certain things over and it works itself out. Oh, this is tricky to talk about. Now, here's the thing. The first 3 share 4x minus 5y on the top. I got to think about process besides solving them. Do I have to solve the systems or can I work things out in different ways that's not tricky to you guys? Because there are some times that I can like these are all the same on top. This one is a rewrite. So this equation here, if I multiplied by -2, I would get this equation right there. So I'm seeing those as equivalent. And this one right here is obviously identical to that one. So these are the same. These are the same. But this one is different from that one. You can see this equals -1, this equals 2 with the same, well, that's not the same expression, but it's an opposite expression, which still doesn't work. There's nothing I can do to multiply that one and match it. This one looks like taking this top equation and tripling it, and then we get this one right here. So that's also the same as well. So what I'm seeing is these are the same. I think these three are the same. I think this one's different. This bottom equation does not work like the other ones do. So I'd say these ones are good here. Boom, boom, and boom. That's how I'm going to go with it. So without actually solving, it's manipulation of those equations to see which parts match. This one's unique. That one's like a no solution. If I graph this one right next to this one here, they'd be parallel lines. Last one, number 10. The graph shows the amounts Y in dollars that a referee earns for refereeing X high school volleyball games. Does the graph represent a linear or nonlinear function? Explain. They appear to be linear. If I were to go by actual scales, these are going by 30s and halfway between it's like 45. So 45, 90, 135, 180. I think these are going by 45. So I can state linear there. Not just I can draw a line through it. As X increases by 1, Y increases by 45. Constant rates of change, therefore, make it linear. Part B. Describe the domain of the function. Is the domain discrete or continuous? So, again, I think this was chapter 3. I don't know. But they didn't connect dots. They wouldn't connect dots here. I don't like that they asked the discrete versus continuous after the fact. I want to say discrete first. Discrete because, now here's the thing. You can only have integer amounts of games. The only whole number games are possible. Not like you referee half the game, you make half the dollars. You either make the money or you don't. You either ref the game or you don't. C, write a function that models the data. Now keep in mind for these functions here, oh, should we do a sequence? No, they do Y and X. Okay, they do Y. All right, pretend like there was a line that went through it. What's going on here? Well, if you don't work any games, you don't make any money, and that would be in, as a part of this rate. So it looks like Y increases by 45. That's the slope. So that's Y equals 45X. Rate per game times the number of games equals total amount there. And then part D, can the referee earn exactly $500? Explain. So exactly. So we have to set this equal to that and then divide by 45. X equals 500 over 45. Now let's triple check that. I'm going to say no because 495 divides, but not that. So it's 11 point. I'm going to try this in my head first. This is 11 point. What's 5 over 45? That's 1 over 9. 11.1 repeating, I think, is it. So I'm going to check that right now. Let's do 5. I messed something up here when I was trying to do 22.75 minus the previous answer. But 5 over, excuse me, what am I doing? 500 over 45. 11.1 repeating? Ah, there it is. So it's not a whole number. So 11.11. Can they earn exact $500? Explain. No. I mean, I don't know what to explain here. If Y is 500, then X equals about 11.11, which is not a whole number. It's not in our domain. That's 11 and 1/9 games. I should say 11 and 1/9. 11 1/9, so I should do the fraction. Okay. All right, guys. That'll do it for this one. This is Mr. Robinson. Thank you so much for watching for this chapter, test, and cumulative assessment. Coming up next is chapter 6 on exponential functions. Ooh, we're going to get into a whirlwind there. Get ready for section 6.1. It should be a doozy because it's a brand new set of kinds of algebra. We're using x in an exponent now. Looks way different from what we've had before. Anything you learned before, you might be able to ignore now. All right? So take care. I'm going to see you in that next one.